Hi everyone, so we're going to continue on the quantum mechanical topic, and here we're going to still continue on talking about experiments that led to the theory of quantum mechanics. In the first couple of concepts we talk about blackbody radiation, and then of course we came up with Planck's equation, which help us determine the energy quanta, or the kind of quantity of energy that has to be absorbed or released by light, okay, when matter and light interacts to transfer energy. And then we talk about the photoelectric effect, which is Einstein, um, really revolutionary idea about how light interacts with matter in that case. And he proposed the idea that light actually, in that context, doesn't really behave like waves as previously thought, but behaves as a bunch of particles, and each particle has a certain amount of energy. That energy is given by Planck's equation. E of the photon, which is the light particle, is equal to h nu, and the light particle has a certain amount of energy. That energy is being transferred to the electron. If there's enough energy in the light particle, one electron that interacts with the light particle can then be ejected off the surface of the metal. Okay, now we're going to talk about the third major discovery and model that sort of led to this idea of quantization of the energy of the electrons as well. And this is referred to as the atomic emission spectra. That's the experiment, and then the model that was proposed is this Bohr model of the hydrogen atom. Okay, so we're going to talk about that now. And the first one, I just want to kind of talk about this idea of the atomic emission spectra. So what is atomic emission spectra? Well, it turns out that if you have atoms, or really if you have, even a lot of different types of objects, right? When they, when electrons in these atoms are excited, or they receive some energy, really that term excited really means they receive some energy. These atoms or elements, or the sample of matter, can emit light, right? And this is really, what we're talking about when we're talking about blackbody radiation before, right? We're saying that sample receives some kind of energy, and that energy is then being emitted in the form of light. And then remember that we talked about the fact that with the blackbody radiation we have certain, corresponding wavelength or color that's observed depending on how hot that particular object is. So if you're doing this with atoms and elements, you can also get that. So you don't necessarily have to do this just with substances, like in the case of blackbody radiation we talk about all kinds of stuff like sun, and other stuff, but you can also have atoms and elements emit this light. Okay, so it turns out that the difference is that if you have something like the sun, for example, right, emitting light, and you take that light and you split it by a prism. Remember that we can do that. We can see the spectrum of, which is basically the components of the light that comes from the sun. And what we notice is that light is composed of what we refer to as a continuous spectrum, meaning that all of the light, the different colors of light of the rainbow, compose that white light that comes from the sun. Okay, all light is present. It turns out that if you were to do this not with sunlight, let's say you do this with something like neon, if you take neon gas that's hot, that's been heated, and you put a prism on one side to try to see what kind of light comes out on the other side, it turns out that you don't see things like this, but what you see is only certain lines. Okay, you see lines here, as opposed to a continuous spectrum. You see only certain lines. The rest of it is just dark. Okay, so it's sort of like as if nothing is in between, and then you see one line corresponding to one wavelength, the red wavelength in this case. You see another line, yellow, corresponding to the yellow wavelength. You see a couple of greens here corresponding to the green wavelength. Then you see a cyan color. You see a couple of blues here at the end. Okay, so that's what we refer to as the emission spectrum. And a lot of times this, by the way, it's also called a line spectrum, to differentiate that with the continuous spectrum, because they're both emission spectrum, but then in one case you see a continuous spectrum, in the other case you see a line spectrum, because you only see certain lines showing up. You don't see all the other colors showing up. Okay, now I want to mention this on the side here. There's also something called the absorption spectrum, which basically corresponds to the spectrum with the emission lines taken out. So it would look something like this, right? So you can see that for for this specific elements, the emission spectrum looks like this. Only certain lines are emitted. The absorption spectrum, basically what this is saying is that this particular gas absorbs everything except for those lines that are whited out in this case, okay? And you can do this experiment the following way. You can basically take these gases that are, let's say you put them in these light bulb, okay? And you can actually do, there's light bulbs that are sold like this. They're composed of gases. You also have these, they used to be called halogen light bulbs that you can put into your lamp, and they're very bright, but they're basically set up the same way. So inside this glass tube, there's a gas, okay, and it could be neon, it could be hydrogen, could be helium. And in fact, this type of stuff, these lights, we usually call them neon lights for that reason, because they're composed of neon usually, because neon has very reddish orange color, and that's the one that people like to use to light up billboards or other types of signs. Okay, so you take that gas that's heated up, and you heat it up by putting electricity. So you basically connect this to a source of electricity. And then the gases are heated up, and when they're heated up, then you see certain glow coming out of that gas, okay? If you pass this through a prism, okay, like here for example, then that prism can split the light that you observe from the heated gas into many different components. And like I said, usually if you start with white light, what you see is a continuous spectrum. But if you start with something like a hydrogen lamp, for example, then what you see is just certain lines, as illustrated here in this film. Okay, so you only see one line, two lines, three lines here, but you don't see the rest of them is just dark. Okay, there's no other color being observed. This is actually, let me just show you this movie here to show how this is done. So what this person is going to do is basically he's going to put a source of light, in this particular case hydrogen gas, and then he's going to put what we call a diffraction grading, and I mentioned this idea before in when we talk about waves and lights at the beginning of this topic about diffraction grading. So if you forget about this, you can take a look back at that topic again, watch those videos again. But the diffraction grading basically acts like a prism. It allows you to split the light that goes into the different components. So let me just show you what he did here. So he took, so you saw there, that was your hydrogen lamp. And this little square here is the diffraction grading. And basically the component in diffraction grading allows him to split this light into its components. And as you can see, what he's showing here is that this is the component of hydrogen light, okay? The light here that you see, it looks a little reddish, is composed of all these three different wavelengths only, okay? At least the ones that you could see, the red, the cyan, and the blue, okay? There's actually another color here, but it's usually a little harder to see, a little greenish color, but it's a little harder to see, okay? Let's go to the next one. Just to kind of show you this idea that you can split this light using the diffraction grading, okay? So he's going to use now, he just did hydrogen, he's going to do helium now, okay? So this is helium, right? That's just the light that you observe from helium. You can see there's a little orangey. If he split it, now you see that that's all the component of helium, okay? There's a bunch of lines now. Helium has more lines than hydrogen, okay? So it's interesting because obviously from here you can tell that depending on the elements, you might have different number of lines and different colors as well that make up that particular element. In fact, I'm going to close this presentation with that concept, okay? So helium showed a different set of specific wavelengths, and he said here that astronomers use these spectral fingerprints to determine what stars, planets, etc. are made of, okay? So for example, you can take a look at light coming out from a particular star, for example, and then you can then split that light into these different components. And then if you notice that it matches helium, for example, like majority of it matches helium, then you'll say that, okay, this star contains primarily helium with a certain percentage of hydrogen or something like that, okay? But that's kind of the idea of how you can actually use this piece of information to learn something about, extra terrestrial materials like stars, planets, and so on. Okay. Now you can see here Mercury can also do something like this. That's Mercury, and then you see very bright lines here. There are 3 lines here that are very strong. There's another line here. It's a little hard to see, but there's 3 lines that are very strong. That's from Mercury. Okay, so hopefully you get the idea now that these these elements, they can generate these lights. Okay, these lights, and then the lights can be split into different lines, different wavelengths. So just reiterating the idea that I mentioned earlier, that line spectrum of an element is its fingerprint. So you remember that maybe in the previous chemistry course you used to do this thing called a flame test. The idea there is fairly similar, which is that an element basically has a specific type of color that it would generate. Okay, and we use that quite a bit to identify the element, like I said earlier with the example of stars and planets. So you can also use this to identify element. For example, sodium usually tend to have a yellowish color. Potassium tend to have a bit of a bluish, purplish color, and so on. So we can use that to identify the different elements. And in fact, in fireworks, when we do fireworks, basically we're combining all these different elements to generate all these different colors of light. Okay, because again, each element would generate a specific color of light. That light is actually composed of specific wavelengths. Okay, that you can split up using either diffraction grading or a prism.